Okay. Today we're talking about, well, first I'd like to get back to this issue of escape velocity because it's rather interesting. And it relates to both black holes and also a lot of what we do in the space program. So let's talk about this. I'm going to do a little math that's not required for you to pay attention to. But my sense is about half of you will want to follow this anyway, and the rest of you need to know the results. I wrote down an equation last time that the force on an object of mass m is proportional to that mass. It depends on the mass. It depends on the mass of whatever is pulling you, in this case the Earth. It goes as r squared, where r squared is the distance to the center of that sphere. And this is the so-called inverse square law. And then to get the units right, there's this constant. And that constant can be measured by taking two small masses and seeing how much they attract. It's not very much. You take 2 kilogram masses, and as I recall, the force of attraction is less than the weight of a flea. That's why we don't particularly notice it. We only notice it for the Earth. Because the Earth is so big, it makes this force big. The force that it makes on us, we call our weight. Now, physicists like to make a distinction between mass and weight. Mass is the thing that makes something massive, and it's the thing that makes it hard to accelerate. Because you have to put a force on it to accelerate it, and F equals ma. And if it's a big mass, then you need a big force to get the same acceleration. So that's what a mass is. In space, things have mass. Weight is a term, they're used interchangeably by the rest of the world. So this is a physics jargon. We like to use the word weight for the pull of gravity. Something that's more massive will have more weight. And so we tend to think they're the same, and they almost are. If you're always on the surface of the Earth, it really doesn't make that much difference. They're almost the same. The kilogram is a unit of mass. Okay? To the physicist, it's not a unit of weight. But to everybody else, it's a unit of weight. You have something that's a kilogram, and that's the mass, and it will actually weigh about 9.8 newtons. I'm not going to ask you to learn all these units. Future presidents don't need to know newtons. But when they sell it to you in the supermarket, they'll sell it by the kilo. A kilogram is about 2.2 pounds. So everywhere else in the world, except in the United States, they sell things by kilos. 2 pounds. You got to know that. Just if you're going to travel, you have to know what a kilo is. So it's about 2 pounds. And they'll use a gram, which is 1,000th of a kilogram. A penny weighs about 3 grams. A nickel, I like that. Nickel weighs 5 grams. Easy to remember, right? 5 grams, 5 cents. So that's what a nickel weighs. So a cubic centimeter of water is 1 gram. That was the original definition of a gram. But some things weigh more. And the general public uses the mass and kilogram interchangeably. But in these equations, you have to be careful. I'm not going to teach you how to be careful. That's one of the things you spend a lot of time on as a physics major, is learning how to plug in the right units to get the right answers. And I don't think we have time for that in this class. So, as I said, if you ever need to plug in, just hire a physicist, and they'll do it for you. This then gives you the force. But this is important here. The more massive you are, the bigger will be the force of gravity. Now, suppose you want to take this thing and take it to the nearest star. You have to lift it up against, you have to do work to lift it up. How much energy does that take? Again, there's a very simple equation for this, which I'm not going to ask you to use because that's not the important thing. But the energy is equal to the force times the distance. That's it. So you want to know how much energy it takes to take it to space? Well, there's this weight, and you keep on going, and you're going an infinite distance. It sounds like it's going to be an infinite amount of energy to take it to space, but not so. The reason is the force gets weaker as you get further away. So by the time you are, instead of right now you're at 1 Earth radius, by the time you're at 2 Earth radii, the force is 1/4. So it's getting easier to lift as you get further and further away. Get to 3 Earth radii, and the force is 1/9. So the force is getting smaller. As a result, it doesn't take an infinite amount of energy. In fact, now this is what calculus is. Calculus is, if this thing is changing, how do I get the total energy? Because the force is changing all the time. And I just can't add up multiply the force times the distance. Well, that's what calculus does. So any of your friends who have studied calculus, this is the kind of problem that we love. And it turns out the energy to get something to infinity looks like an equation very similar like that. It's mE g over r, radius of the Earth. That's the energy it takes it to go to infinity. You get from here to here using calculus. You don't have to know any of these equations. I just thought you'd find them interesting. So we can calculate how much it takes to get something to infinity. There are two ways you could do it. You could lift it up a ladder, and that's called skyhook. Skyhook is this idea of actually building a Tower of Babel that goes to space, and you can just carry things up. The advantage of skyhook is that you don't need rockets. And rockets are extremely wasteful of energy, as I will show. That's really a lot of what this lecture is about, how terribly wasteful they are. A space shuttle uses 22 times more energy. 22 times more energy than it would take if you lifted something up in an elevator. And the space shuttle doesn't even get to space. I mean, it gets only halfway up. Okay, and the efficiency gets worse as you try going to faster speeds with an ordinary rocket. You'll see why. So this is the energy it takes to get to space. Now, we could lift it up on an elevator. Another thing we could do is shoot it out of a gun. Let's forget the slowing effect of the Earth's atmosphere for now. That makes things more complicated. Shoot it out of a gun. How much energy would it take to get it to infinity by shooting it out of a gun? Fascinating answer. Exactly the same. Doesn't matter whether you shoot it or lift it. It's the same amount of energy. A way of thinking about this is, suppose you shoot it out of a gun. It takes a certain amount of energy. It gets to infinity. Now someone says, let's just hold it here for a moment and release it. It's pretty far away, but it'll gradually start to fall. As it falls, it goes faster and faster and faster and faster until it hits the ground. The energy it has when it hits the ground is equal to this. This is what's called conservation of energy. This is sort of an abstraction. And I'm not going to ask you to work out problems like this. It's just that this is the sort of thing that enables a physicist to sometimes answer questions very quickly because he knows energy is conserved. So lifting it up is fine. Doesn't take much energy. Shooting it from a gun, if you can do that efficiently, takes the same amount of energy. If all the fuel goes to accelerating the bullet, that's good. Rockets are terrible. They take 22 to 60 times more energy than that. Why do we use rockets? Well, we use rockets because we're still in the very primitive stage of space travel, and that's the only thing we have that can get us into space right now. We'll be talking about that all throughout today's lecture. Well, this is interesting. So this is the energy that it takes. Now, suppose we do it as a bullet. Again, I'm going to do a little math here that you're not required to know, but I want you to enjoy this. Suppose I shoot it as a bullet. Then the energy I have to give the bullet is equal to this. That's the energy of the bullet. Energy of the bullet is 1/2 mv squared. Now take a look at this equation. And let's solve for the velocity. So we can solve for the, oh look, the m's cancel. And then you put the two, the velocity doesn't depend on the mass of the bullet. Isn't that interesting? This is one of the key things I want you to know. You're going to shoot something into space, the velocity doesn't depend on the mass. That's why we use the term the escape velocity. Escape velocity means it doesn't matter what mass the object is, it has to get going to 11 kilometers per second to escape. If you get it to 11 kilometers per second, it will escape. In fact, this argument is so general that there's something even more strange and counterintuitive, and some left over from somewhere. Here's the Earth. And again, we're ignoring the atmosphere because you've got to get that 100 kilometers up so the atmosphere doesn't slow you down because that's just wasted energy. Any energy you get pushing air aside goes into heat. And that's a problem, actually. But suppose you have the Earth and you want to shoot something to space. You can shoot it straight up. And if you shoot it at 11 kilometers per second, it'll slow down as it's moving because gravity is pulling it back. But gravity is getting weaker. And so as it's getting away, here I'm going in this direction. Okay, I'm still slowing down, but I'm not slowing down as much. My acceleration is less because I'm so far away. The gravitational force is down by 1/r². It's getting weaker and weaker and weaker and weaker. And escape velocity is when as I get to infinity, my velocity gets to 0. In other words, I never really stop, but I slow down a lot. That's the escape velocity. That's 11 kilometers per second. Now, here's the interesting thing. Suppose instead of shooting it this way, I shoot it this way, sideways. Well, then it'll curve its path like that. What velocity do I need if I shoot it sideways? The answer is the same. So this argument didn't depend on what direction it was. These are one of the lovely things that physicists just drool over. This gets a physicist as excited as, well, let me not make an analogy. The escape velocity doesn't depend on direction. Now, of course, this is not a good way to do it because you wind up going through more atmosphere when you go that way. But on the moon, it doesn't matter what direction you shoot it. You shoot it at the escape velocity for the moon, which I think is, I don't remember what it is, but something like 2 kilometers per second. And it doesn't matter what direction you do. Now, there's also the orbital velocity. That's the velocity it takes to go around like that. That's pretty high, too. That's 8 kilometers per second. Okay? Whereas the escape velocity for the Earth is 11 kilometers per second. So escape is more because you're going further away. Now, an interesting thing about this, and again, this is an amusement for all of you here. I'm going to be using this fact, but not require you to know it. I want you to know that escape velocity is higher than orbital velocity. It's always a little bit higher. How much higher? It turns out to be higher by a factor of 1.414. You may recognize that as an approximation to the square root of 2. The energy to escape is exactly the square root of 2 bigger. You can show that using calculus. It's not hard. I'm not going to bother doing that. So it's a factor of 40% bigger to escape. And that's true whether you're escaping from the sun, the moon, the Earth, or Pluto. Escape velocity for Pluto is very small. For some of the asteroids, you can escape by jumping. Here's the escape velocity. That makes it hard to walk around on an asteroid. Gravity is so. You saw them on the moon. The old films of the astronauts going. It amuses me that prior to landing on the moon, you cannot find a single science fiction movie that depicts that correctly. Science fiction is amazingly bad at visualizing what's going to happen in the future. I sometimes collect old people who call themselves futurists are particularly bad. I would be ashamed to call myself, if someone called me a futurist, I would make a libel suit against them. Because futurists have such a bad record. My favorite, though, I have a slide of this I could show, is a picture done in 1914 of humans finally getting to the moon. And so how did we get to the moon? How did they imagine we'd get to the moon in 1914? It's really funny. I have to bring this in. What they imagined, the two high technologies of 1914 was the big ocean-going liner and the airplane. So the futurist says, ocean-going liner, that's really high-tech. They didn't use the word back then. And said, airplane, wow, that's only been around for a few years, and it's amazing. So what they had this wonderful painting of men and women going to the moon, and they're standing on the back of an ocean liner that has a biplane's wings on it, and that's how you get to the moon. So when if anybody calls himself a futurist, keep in mind that's about how accurate they are. I think science fiction in general is much better at predicting the future than are futurists. That's because they have to make a really realistic story behind it. In H.G. Wells' From the Earth to the Moon, he talked about shooting a bullet to the moon as the way to go. That's much more efficient than using rockets. The only problem is you accelerate this bullet so much that the virtual gravity, the gravity that someone inside the bullet will feel, if you accelerate it at the Earth's gravity we call 1g. And that's 22 miles per hour per second. But if you're going to accelerate it to escape velocity in the distance of a gun, you have to accelerate it much, much more than that. That means anybody inside of that rocket will feel an enormous virtual gravity. They'll be crushed against the bottom. This is the main problem with shooting things to space. It's not just humans who would be crushed, but all electronics as we know it. There's an invention called the railgun, which we'll talk more about, which is a way of accelerating things much more efficiently than a rocket. The trouble is it's a gun, and so you have to accelerate things in a short distance. Accelerating things in a short distance to high velocities mean that everything inside feels this g-force, which is much, much greater than ordinary gravity. And in every case that I've looked at, where you're getting up to the kind of high velocities that people brag about, the only thing you could put in there is a piece of steel. Because you put in any structure, it just gets crushed by the gravity that you would have. So we'll be talking a lot more about railguns. You'll see railguns in the news. If you see one in a newspaper article, that's a great homework thing to use. A railgun is a gun used to accelerate things to very high speeds, higher than you get with rockets. Still haven't told you what the problem with rockets is, but we are getting to that. So this is the escape velocity. Suppose we have something that's so massive. So suppose this. The escape velocity there, I have v squared is equal to 2m of the object times g over r of the object. That's the escape velocity, okay? Suppose we got something which was really big in mass and very small in radius. Then the escape velocity would get very big. How big? Well, let's pick something that's so massive and so small that this turns into c squared. So the escape velocity is the speed of light. Then even light wouldn't escape, and we'll call that a black hole. And this is, in fact, the black hole equation. You want to know if you're a black hole? All you need to know is how big you are, your mass, and how small, compact it is. And if this is true, or if it's even bigger than c squared, then you have a black hole and nothing can escape. The derivation I just gave is a little bit sloppy because I made some assumptions. I basically was assuming that this equation is still true at high velocities, which it isn't. But it turns out this is the equation for a black hole anyway. This is the exact equation for a black hole. So mistakes tend to cancel when I do this, but the sense is right. If you need to escape, you can't go faster than the speed of light, and the reason is it would take infinite energy, as we will show when we get to the theory of relativity. Infinite energy means more than the energy in the universe. That means nothing left for you to watch because you put all your energy into this bullet, and at the same time, you won't get there anyway because that wasn't enough. So black holes, you cannot escape from a black hole. But think of black hole as the situation when the escape velocity is the speed of light. It even gives the right equation. And that's what a black hole is. We'll be touching on black holes over and over and over again. Before class, we had a discussion on whether we are living inside of a black hole. And for a long time, many people thought we were, but the best evidence now is that we aren't, and it's amazingly difficult to tell, because we're not trying to escape the universe. In fact, you can't escape the universe. So the fact that it's the inside of a black hole is possible. So now, I mentioned the square root of 2. Let's take a look at another orbiting situation, one that was in the news recently, and this is the trip to Pluto. The Earth is going around the sun. There's the sun. Actually, this distance is 100 times bigger than this diameter of the sun, so it's not drawn to scale here, but we're going around the sun. Think of this as orbiting the sun, which we are. But suppose we want to go to Pluto. Pluto is 40 times as far away as this. 40 astronomical. That's pretty far out. That's almost infinity. So suppose we want to go to Pluto. Then what we have to do, this velocity isn't enough. You send a spaceship away from the Earth, it'll still orbit the sun. So imagine now we have a spaceship orbiting the sun, but we want to send it to Pluto. What you need to do is get a higher velocity. How much higher? Well, this thing which has just left the Earth and is orbiting the sun, going about the same rate as the sun, is 30 kilometers per second. That's a lot faster than escape velocity. That's why it's still orbiting the sun. The sun has a lot of gravity. Suppose we want to get to infinity. We have to make it bigger than that. How much bigger? Square root of 2. So if we wanted to escape, instead of 30, it's 30 times the square root of 2. So what is the square root of 2? 1.4 times 30. So let's do it this way. Times 30 is 0, 2, 3. So it's about 42 kilometers per second, if I did that right. 12, 34, okay. So what you do is you add that velocity to the velocity it already has, which means you don't shoot it this way, because then you're not making use of the existing velocity. You shoot it in this direction, and you make it go an additional 12 kilometers per second. So you shoot it like that, and then it'll go all the way to Pluto. So this is at 42. So you get into space, and then you still have to give it an extra 12 kilometers per second. Well, to give something 12 kilometers per second, I mean, you look at the rockets that we use to send things into orbit. And now we have to have a rocket like that up there to accelerate it even further. It's very hard to do. This is why we only send little things to Pluto. Not only that, but at this speed, it's slowing down as soon as it gets away from the Earth, because it's using up that energy to get away from the sun. Just as you slow down because the sun's gravity is pulling it back, it's slowing down, and so it gets slower and slower. If you want to get there in 10 years, you have to give it even more velocity. So they had to give it a very high velocity just so it would get to Pluto in 10 years. I don't remember what the exact velocity was. Maybe someone here wrote on it and remembers. But that required a very special program. Why 10 years? Because you don't want to build an instrument that will send back a signal in 30 years, because by that time you're retired and you don't get any of the fun of all the building that you did. Also, it's hard to build instruments that'll last for 30 years. So they got more speed than necessary just so it'll get there. How do you get energy to broadcast back for 10 years? You use plutonium, actually. You use something called a radioisotope thermal generator. We'll be talking more about that. It's really the only practical thing you can use. It's actually a plutonium that does not, it's a kind of plutonium that does not work in atomic bombs, does not work in a nuclear reactor. It's a plutonium that's just radioactive, but will not undergo a chain reaction. We'll be talking more about that in, I guess we start radioactivity, what, next week? So we'll be getting to that. So that's how you get to Pluto. By the way, here's another interesting aspect important for presidents to know. When you're launching a satellite, do you launch it from the East Coast or the West Coast? Many of you probably guess. That's called a rhetorical question. Many of you will probably guess that you do it based on political considerations. You know, which has more powerful senators on the East Coast or the West Coast? Turns out there's a very good physics determinant. And here's what it is. Here's the Earth. And let's say we're looking at it from the North Pole down. And the Earth is spinning. Now, you know the sun rises on this side. And that means the Earth is going this way. So this is the North Pole, looking down. So the Earth is moving that way. And now here you are, and you want to launch something, which means you want to give it, oh, let's say escape velocity, just to make it easy. Well, the Earth is already rotating 24,000 miles on the equator in 24 hours. It's going 1,000 miles an hour. That's something like 0.4 kilometers per second. So if you're going to launch it, it's already going 0.4 kilometers per second. Let's say you want to get it up into the orbital thing, it's 8 kilometers per second. You don't have to get it going as fast because it's already moving in that direction. So you want to launch towards the east so that you can take advantage of the spin of the Earth. Well, hey, you could launch it from the west and take advantage of the spin of the Earth, right? Yeah, but then you're launching over populated areas. So they launch from the East Coast so they can take advantage of the spin of the Earth and yet launch it over the ocean. Now, there's an exception. If you want to go into polar orbit, that means you want to orbit this way, above the North Pole. If you're going to do that, you can't have any component of velocity this way. You have to take off the spin of the Earth. That makes it harder to send it into a polar orbit. Basically, going into polar orbit, here it's spinning here, it has no horizontal velocity. So they actually have to launch it in the opposite direction. They have to launch it towards the west to take away the spin of the Earth, and then towards the north to give it the polar orbit. If you're going to launch it to the west, you have to launch from the west coast. And so the result is our polar orbits are launched from California, and our non-polar orbits are launched from the east coast. And that's the logic behind it. So it's not all political. Okay, now let's finally get to rockets. I had this little demo I showed last time. The key thing here is F equals ma. And that means if you have a force, you have an acceleration. How fast are you going? It depends on how long the force is there. So the speed depends on the force. That's an acceleration. You're going 22 miles per hour every second with gravity. If you keep on falling for a long time, you get going faster and faster and faster. So the key is a force doesn't give you a velocity. A force gives you an acceleration. You have to apply that force for a long time to get things going. It's a simple demo here. And here we have a card, very low mass, and a weight, which is, actually it's not really very heavy either, but it's heavier than a card. I put that here. Now what I'm going to do is hit the card with a force. It'll be enough force that I can knock the card off this thing. Okay? And now I'm going to put a weight on top of this. Now what's going to happen is this thing doesn't actually hit the weight. It only hits the card. But the card is sitting, the weight is sitting on the card. And so when the card starts to move, there's the force of friction. Now the card, as you see, gets going pretty fast. And as a result, that force of friction lasts for only a very short time on the weight. Because this weight has a lot of weight, it has mass, it doesn't get going very fast. This is a good thing for you to think about and discuss. It surprises some people that when I do this like this, the card shoots out and the weight goes straight down. But think about it. You don't need the equations to understand this. What you need to know is that the force of friction on this thing lasts such a short time sometimes not short enough. Okay. I have to get this right on top of it as part of the problem. I think it's all right. So think about that. It's a good thing. You probably haven't seen this demo before, but you may have heard about this one. It's the same demo, right? If I pull this fast enough, it's light mass, so I can pull it really hard and get it accelerating really fast. That puts a force of friction on these things, but these things are more massive. And so if I do it fast enough, they will accelerate just a little. They get the acceleration, but for such a short time that they don't get going very fast. And by the time they're moving just a little bit, this is gone, there's no more force, and they just stay there. So if I do this just right, I get right about half the time. Students are always hoping I don't. If I pull this just right, I can pull it out from under there. We don't have any expensive wine glasses, you'll know. We used to, but they're all gone. And I should be able to pull this right out from under it if I have the courage and do it suddenly enough and fast enough. Yeah. You would have applauded so much more if it went crashing. Okay. So that's applying F equals ma. But now let's take something else. Imagine you're in space. And you're sitting there. And you want to go somewhere. There's nothing to push on. No ground, no wheels. What do you push on? Well, here's the solution. You take a piece of chalk. You put a force on that chalk. There's a force on your hand. You feel it. So I put a force on that chalk to accelerate it, but I feel a force in my hand. I probably can't tell the difference, but it's just a force. And therefore, I'm being accelerated this way. And so if I had enough pieces of chalk, I'd throw one that way, and that would get me going a little bit. You've experienced this. You know, if you anybody who's fired a gun, a big gun, you shoot. You know, you stand there like this, boom, and you go flying backwards. The bullet's going that way. Inside the gun, there is this gas that's expanding. It's putting a force on the bullet. The bullet's small, so it accelerates a lot. You and the gun are big, so you don't accelerate as much, but you do accelerate the back way. And if it's a big explosion, big gun, you fall over. So you got to really brace yourself. Even if you brace yourself and you're not experienced, you could at least damage your shoulder because the gun goes backwards so much. Now, let me derive a little result. And again, I'm not going to require you to know this derivation, but for many of you, you'll find this interesting. We're going to use F equals ma. When the bullet is firing from the gun, it's inside this thing, the bullet is shooting out. There's a force on the bullet as long as it's in the barrel. That's why the barrels are long. That's why a longer barrel gives you more range, because you keep the force on the bullet for a longer period of time, and therefore it accelerates more. As soon as it's out, it doesn't accelerate. In fact, air pressure makes it slow down a little bit. Air resistance. So here's the explosion. It's pushing on the bullet. It's also pushing up, but it's also pushing down. So you don't feel up and down because the explosion is pushing at the top and pushing at the bottom. It cancels. It's also pushing backwards, and there's nothing canceling that, so that's why the gun goes backwards. That's the recoil of the gun. You shoot a gun like this, the bullet goes forward, this goes backwards. The bullet hits a person, and as you know from all sorts of movies, the person then goes flying across the room. At least that's what they have in the movies. In reality, it doesn't go flying across the room, as I'll show you. But here, a little mass is going forward. The force is the same. It's the same force on both of these things. Is that the same acceleration? No, it's not the same acceleration because this is more massive. So this one gets the same force. The acceleration is less. The acceleration is just the force over the mass. There's less acceleration. This one has a bigger acceleration. This one here, the acceleration, I'll use a capital A, is the same force. Let's put a big M here for this mass, the big mass, and this is over the little mass. And the accelerations aren't equal. The forces are equal, not the accelerations. The accelerations work for the same amount of time. So if they all work for the same amount of time, the velocity will be equal to the acceleration times the time, and that's going to be equal to the force divided by the mass times the time. You don't have to know this. This velocity, this is a small velocity, this velocity, this big velocity, is going to be equal to the big acceleration times the same time, and that's going to be equal to the time times the same force divided by the little mass. Now, let me rewrite these two equations in the following way. I'm going to write, I'm going to say v times m times little m. That's little v times big M, sorry. This should have been a big M here. I apologize for that. So now I'll write this equation as big M times v is equal to force times time. This equation I'll write as little m times big V is equal to force times time. My God, they're equal to each other. Big M times little v equals little m times big V. So that's a derivation that you don't have to know. But here is the consequence. If this thing weighs 20 times as much as the bullet, then it will be moving 20 times slower. It's just a ratio of masses. There actually is a bullet in here. And so when the gun goes back, it's moving slower just because of the rifle, and presumably because of you too. So you get there to hold this thing, so your mass counts also. And if you brace yourself just right, you get the whole mass of the Earth. So this is why you brace yourself, and then you get a really fast bullet. Now the bullet comes out much faster, but the velocity times the mass is the same as the velocity of the mass times that. Well, these are details. I'm not going to ask you to calculate with these things. But now watch the following. We're going to shoot the bullet into a block of wood. Now this is massive. It's big. The same thing happens. Here you have a mass times velocity. This is now a big mass. This is a process that's called momentum conservation. Physicists love it because it enables them to calculate things. You hardly need it for anything except for a conceptual picture of what's going on. Because this is so massive, it will have much less velocity. In fact, this thing looks like it's almost as heavy as the gun. And so here we have slow gun, fast bullet, hitting this, and then this will be slow rebound. In fact, because the masses are about the same, the rebound should be about the same. When I fire this, what I'd like you to notice is that this thing swings about as much as this swings. So that's the concept. And when you see someone being shot by a bullet in a movie and they go flying backwards, it's hard for me to make sense out of that because the bullet is going really fast, but it doesn't have very much mass. So let's try this now. And as you're watching this, keep in mind the following. This gun shooting a bullet is our model for how a rocket works. When you're in space, you could throw things out. Best if you throw them out fast, because that'll give you backwards motion that's bigger. If you keep on shooting, you keep on accelerating. And that's how a rocket works. The stuff it shoots out is the burnt fuel. What happens is you explode the fuel to release this energy, get the high pressure, and then the thing you push out is the fuel. Boy, that seems dumb, doesn't it? Yeah, but it's the only way we get to these velocities. Because you can keep on throwing that stuff out. This is why the space shuttle rocket, when it launches, is 22 times heavier than the little space shuttle that actually gets into space. You're carrying all this fuel just so you can throw it away after it's exploded. And you can say, well, just carry up mass. You can throw that out. Sure, but as long as you're carrying up mass to throw out, you might as well make it into fuel. So you get the energy that you need too. This is what rockets do. Really dumb. But it's the only way we get to high velocities because you can keep on going. You keep on getting faster and faster and faster and faster. So let me get, this is designed so that I don't have to put my finger on it because we want to see the recoil. So what happens is I can fire this bullet by burning this cord. Now let's see. Should be all set. Let's see if it works. If I burn this cord, watch, see the shaking? They're going about the same. And now there's a bullet in there. Okay? So, that's a rocket. That's a gun. Rockets work in this totally ridiculous way. One of the questions at the opening of the chapter I got an email about from one student. I said, I remember reading a newspaper by a reporter who hadn't taken this course because it didn't exist back then, that in space, he thought, you're massless. No, you're not massless. Your mass doesn't change. There's no weight, but you're not massless. And so, he said, even if you sneeze, the air coming out will shoot your head back at a high velocity and give you whiplash. And that's nonsense in several ways. One of them is that for one, you're not massless, so the mass of your head is very big, not small. And so if you do act like a little rocket, your head wouldn't go back that fast, but certainly no faster than it does here. Now, someone emailed me, one of you emailed me, and said that in their experience, heads go forward when you sneeze. And that's right, of course. And I know a lot about that, it turns out, because of an observation I made when my baby Betsy was about 30 minutes old. I watched her learn how to sneeze. We were at the hospital. I was there at the delivery, and my wife had some minor complications, so they had me hold the baby. Here I'm holding this baby. It's amazing. You have instincts for babies you don't know you have. You're really designed to have babies. And you may think babies are alien things, what are they? But no, your instincts come out when you have one. And I was feeling very possessive of this baby. And the nurse would come over and say, hey, let me do this. I'd say, with my baby? Well, so I'm holding this little baby, and the baby's there. And then the nose starts twitching. Okay. That's amusing. And then, Baby sneezes. I'm terrified. She's terrified. Her head looks like it's about to be knocked off by the sneeze. You know, okay. And then a moment later, oh my God, here comes another sneeze. And the baby feels the same way, little baby Betsy. I mean, here she is, less than an hour old, and you could see the fear that she has that she's going to go through this terrible thing again. And so what she starts doing is crunching up like this, and then she sneezes. It's okay. She learned how to sneeze. I actually watched my daughter learn how to sneeze. You start learning at an amazingly young age. We were both relieved. The next sneeze came around, she went like this. So she had it mastered just after that first half hour. So I think the reason many of you think you go forward when you sneeze is because your instinct is to go forward, get prepared for the sneeze in preparation for it. If the sneeze is too small, you wind up going forward. Anyway, that's my guess, based on my scientific observation of my 30-year-old daughter. That's the sneeze. Balloon. Oh, I have this thing here. And let me see if I could turn this thing on. This goes on over here, I guess. Turn on that one. The ideal collision. This is an interesting one. Those of you who have gone bowling have noticed it. Why is that? Why does it just come to a perfect stop like that? The air is just to keep it floating so it doesn't have friction. Right now there's too much friction to see that. But why is it that when it comes like that, this one stops and that one goes? Well, the reason is they have the same force on them. At the contact, it's the same force. So this acceleration equals this acceleration. This acceleration slows this one down. This acceleration speeds this one up. They're exactly equal and opposite. This one slows it. If this one slows it down just enough, we could actually work this out. If the masses are the same, this one will come to a stop. And that same force on this one will take it from a stop to the velocity v. It goes from v to 0. It's slowing down. This one goes from 0 to v. So again, this is the sort of thing that physics majors will spend a week learning how to do the equations on. But you can appreciate what's going on from the equations without me requiring you to be able to do them yourself. This thing here is called momentum, this mass times velocity. And when you're doing calculations, which I don't require of you, sometimes you use energy calculations like for the escape or the black hole. Sometimes you use momentum calculations. There is one other thing that I want to show you on momentum just because it's usually a big subject in a qualitative physics course. And I downplay it. Even though it's fascinating and amusing and delightful, I don't make a big deal of it because I don't really see why future presidents need to know this. But this is angular momentum. Angular momentum is mass times velocity times distance. So maybe you've seen an ice skater or you are an ice skater. And you can all try this. It's easy enough to try. Spin around like this without thinking about it. Pull in your hands. And you go a lot faster. I need a volunteer with strong arms. Who doesn't mind getting dizzy? I'll volunteer with strong arms who doesn't mind getting dizzy. Okay. So I'm just going to demonstrate this effect. And this is kind of, here, you want to hold these? But don't hold them out just yet. Sit in the chair. You probably know what I'm going to do here. So you sit in the chair and hold your arms out as best you can. Now you start spinning. Now pull the arms in. Now out. Now in. Okay. Out, in. So this is what's called conservation. Thank you. He doesn't want to stop. Thank you very much. Ugh. So in this case, what's happening, it's like this momentum, big mass, small velocity. But for angular momentum, it's, what you get is mass. So this is angular momentum, which we're not going to talk much about. Is mass times velocity times the radius. And if you bake the radius in, the velocity has to go up. That makes it spin faster. Where this becomes important is in hurricanes, where the winds are going into a low pressure center. If they're spinning, and they're always spinning a little bit because of the Earth's spin, then they get going faster and faster as they come in. And that's conservation of angular momentum. It's also relevant for space things and so on. Anyway, I wanted to show it to you just because when you see an ice skater, you know, with the Olympics coming up, you watch the ice skaters. So watch this. Watch how they control their spin. They pull all the way in. And it's interesting, when a ballet dancer, some of you are ballet dancers, when you spin, you keep your head facing the same way. Now, that's not easy, but you do, and you do it by going, woo, woo, like that. And some ballet dancers have told me they do this to keep from getting dizzy. It's always amazed me that ice skaters don't do that. They just dance dizzy. I suspect it is possible to just get used to it. I think the real reason ballet dancers do it is that the front of the face is much nicer to look at for most of them than is the back of the head. Now, let's talk about the air. Because shooting off, look at the problem here. Suppose I'm shooting this gun, the gun gets moving. Now I shoot another bullet, it gets moving faster and faster. Suppose the gun gets moving faster than the bullet. Suppose it's moving twice as fast as the bullet. And I still want to get going faster. I keep on firing bullets. But those bullets then, this gun is moving back this way twice as fast as a bullet because it's a rocket. We're going to space. Rockets may move, you know, they may move 1 kilometer per second, but I'm getting this thing up to 8 kilometers per second. And so the bullets are coming out, but the bullets are, even though they're coming out backwards, they're still moving forward because they're not moving as fast, they're not coming out as fast as the gun is going. This gun's going 8 kilometers per second that way, the bullet's coming out at 1, the bullet's still going 7 kilometers per second. So what? Who cares? It's just fuel. Yeah, but it's fuel with energy. It means your energy is being wasted. It means the fuel is not being left behind with zero energy, it's being left behind with energy. It's still moving in the same direction as the rocket. You are wasting energy. And this is the problem with rockets. You put so much energy into the fuel, you don't wind up using it for your own space shuttle. This is why rockets are so inefficient. I mentioned the number for the space shuttle. I think it was a factor of 22. Compared to the energy that you get if you launch it from a gun, which you can't do because of the high g-forces. So they have only low g-forces in the space shuttle. So they launch it at, I think, not much more, less than 3 g's. I think I have the number 2.2 g's or something like that in the text. I looked it up one time. So the astronaut never feels more than 3 times their weight. But because it's such a slow acceleration, you have to do it over 1,000 miles. Can't have a gun that long. Therefore, you have to use the rocket effect. If you could have a faster fuel, if this thing could come out at 8 kilometers per second, then there'd be no problem. When you're moving 8 kilometers per second, that way you fire a bullet and it remains at rest. It actually doesn't pick up any, it doesn't have any excess energy. Imagine if when you're going 8 kilometers per second, your fuel comes out at 8 kilometers per second, it's left at rest, and it's not wasting any energy. So that's the ideal thing to do, is have a fuel that's coming out as fast as your rocket. Now the problem is chemicals, when you explode them, they have typical chemical energies of a certain amount, you know, like 10 calories per gram. You put all of that into motion, and they only come out at a couple kilometers per second. So based on the best fuels we have, hydrogen is better. So hydrogen is often used as a fuel. You want a fuel with the largest backwards velocity as possible in order to not waste energy. And that's the limit. We don't have any fuels that come out faster. There's mention of advanced fuels. Suppose you were to shoot out beams of light. That's going the speed of light. Yeah, it's actually going too fast. It still has energy when it comes out the back because it's going so fast. You want the exhaust velocity to be about equal to the rocket velocity so the fuel is left at rest. People talk about ion engines. The thing about ion engines is you can vary the velocity that they come out. So when you're going slow, they come out slow. Going fast, they come out fast. So that's the problem with rockets. That's why rockets are a technology of our era that sometime in the future people will just abandon except as toys because they're so wasteful of energy. What's going to replace them? Well, you want to push on something else, not your own fuel. You want to use the energy just to accelerate yourself. You like to push on something massive. So typically what you get to push on is the air. And this is the way most airplanes work. Little interesting fact about airplanes. They move forward by pushing air back. They do that with a propeller. What about jet airplanes, you say? Well, people call them jets, but most jet airplanes are really hidden propeller airplanes. What they do is they have an engine inside. It's called a jet engine. A jet engine is something that takes air in and then shoots like a rocket. It doesn't have to carry the air because it gets that from the atmosphere. So it just carries the fuel and it shoots it like a rocket, and that's a jet engine. But most jet engines, I mean, shooting your own fuel back isn't very good. So what they've done now is they add a propeller to the jet engine. They put it here, a propeller. The propeller then is spun by the jet engine. The jet engine makes this rotate around, so the propeller spins like a fan. The fan, here's the air, and the propeller comes around, hits it, and pushes it backwards. And it's pushing the air backwards to get forward. That's what a propeller does. Just like a fan will push the air forward, you take a fan and hold it, the fan will start to move against the air. It's pushing the air backwards. So they add a propeller to the jet plane. Well, you never see the propeller, well, unless you look for it, because they hide it inside the engine. And you look in there, and you will see this big propeller. The planes are called turboprops. And virtually all the airplanes you fly in have a jet engine in the core, but most of the push comes from this fan that's inside of the engine. The prop refers to the propeller. Propeller. So we actually are still flying propeller airplanes, just that they're made very efficient by this kind of a design. How does an airplane stay up? Well, a helicopter you can understand, right? A helicopter has a blade, and the blade spins around, and here's the blade. And as the blade is going this way, the air tends to be pushed out of the way. As this thing scoops up the air comes in and is deflected downward. So you're pushing air down. When you push air down, I'm not pushing very effectively. I don't have very much hand, and I'm not pushing very hard, so there's really not, I can feel a little bit of the air on it, but it's not enough to make me to go up in the air. If I could push down with lots of hands all around, I would fly. That's what a bird does. Birds have a second trick. They're extremely lightweight. Bird bones are hollow. Birds are mostly muscle, except for the birds that don't fly, like ostriches. So a bird flies by pushing air down. If you push air down, there's a force on you. If you make that force equal to your weight, you won't fall. A helicopter does this with a big fan. It's pushing air down all the time. An airplane wing works the same way. Many of you have been mistaught in high school physics that an airplane wing flies by something called the Bernoulli principle. And you were probably mystified by this and wondering, it seems all magical, conservation of energy and so on. And it's really very misleading. Airplane doesn't fly by the Bernoulli principle. I mean, yeah, it does, but it has to. An airplane flies because the wing is pushed forward by the propellers or the turbojet, and then air is pushed downward. By pushing air downward, when I push something down, I feel a force on it. Just like when I push something that way, I feel a force. Airplanes push the air down. Every high school physics book I've ever seen doesn't show that. You're supposed to understand airplane wings? What they always show is here's the airplane wing. Okay, and here's the air coming. And it comes this way. And they say it goes further over the top. Because it's further over the top from our mysterious energy conservation equation, the pressure is less. And because the pressure is less, that lifts the wing up. It's actually not wrong. but it misses the essence of the airplane wing, which is that the airplane wing is deflecting the air, not horizontally like they always show it, but it's pushing the air downward. And by pushing enough air downward, you fly. Same thing in a helicopter, same thing in a bird. One thing that annoys me in movies are they have these giant birds flapping. And the first movie to really get this right was Dragon Slayer. Watch the bird flap. And in most movies, he flaps his wings and flies. It doesn't look like a bird flying. Real bird flying flies like that. Just watch a bird. Okay? Now, what you're trying to do is make sure you don't push air up when you're going up, but then you push it when you're going down. Oops. But because your arms are going down, the body's going up. So when birds are flying in air, they don't even do this right in the Lord of the, I mean, in Harry Potter, they don't do it right either. They have these things flying like this. It just doesn't look very real. But in Dragon Slayer, they had these great big dragons, and they were really flying. So watch birds. Watch birds will become a better movie maker. Now, so everything flies by either pushing fuel down, or by pushing air down, or by pushing the ground down. See, I'm compressing the ground a little bit. The ground is like a spring. And it compresses until the force of the spring equals the force of gravity. And so the spring is pushing me up, gravity is pushing me down, I don't move. You remove the floor, you remove the spring that's pushing me up, and I fall. Air resistance is simply the fact that sometimes you're pushing air and you don't want to. So for example, if I'm on an automobile and I'm driving at 65 miles per hour, there's just air in front of me and I'm pushing it away. The force of air resistance, there's an equation that I'll just write down again, and the main thing I want you to know it's in the book, that the force of air resistance depends on how big it is, the area. And it depends on how much air there is. So that's the density of air. And it depends on how fast you're going, and that's a velocity squared. And the reason is when you're going faster, you're hitting the air harder, but you're also hitting more of it every second, and that's why it's a square. It comes in twice. Not only are you hitting it harder when you're going faster, but you're also hitting more of it. So it's velocity squared. There's usually a factor in here and some other things, but that's the important thing. So when you're going twice as fast, the force of the air is 4 times as great. If you jump off a tall building and spread your arms out, there's a force of air on you. As you get going faster and faster, that force of air gets bigger and bigger. Finally getting so fast that the force of the air equals the force of gravity. So why don't you stop? There's no force on you now. That's why you don't stop. F equals ma. So when there's no force, there's no acceleration. No acceleration means no change in velocity. That's called terminal velocity. Any of you who do skydiving know that you need to increase your area as much as possible. If you make your area the size of a parachute, you'll come down at about 20 miles per hour. And that's what a parachute does. It keeps the area so big that you're running into a lot of air things, and you reach terminal velocity at a relatively low velocity. Big area means you could have a small velocity to overcome your weight. There's a section I wrote, I think it's an appendix, or I'm not quite sure where it is in the textbook, on dropping food out of airplanes. You drop food out of airplanes, this stuff comes down, and it doesn't come down at very high velocity, as long as it's small, because it gets going. It depends on the area, density of the air, but the food doesn't reach high velocities because it very quickly reaches the limiting velocity. We have a demo here that I'm going to try to show. This has 2 things in it. It has a heavy thing and a light thing. The light thing is gold in shape. I wanted to have a feather in there, but didn't get it. And they fall. And you notice the light thing, the gold-shaped things, fall slower. This is usually demonstrated with a feather. And it's simply because this one has a greater force of gravity. So the light one doesn't weigh much. It reaches its terminal velocity when it's going quite slow. Slow is enough to equal its force of gravity, but slow is not enough for the force of gravity of the other one. I'm going to try pumping this out, getting rid of the air, and then the light one, in the absence of air, should put it over there, should go almost as fast. Should go exactly as fast, actually. Now, all I have to do is figure out how to turn this thing on. Let's see, there must be a switch on it somewhere. Okay, so I'm sucking the air out. This, of course, just has a little blade in it. The blade pushes the air by hitting, it's like a propeller on a ship. By going in a circle, it pushes on the air, makes the air go backwards. And so that's pumping this thing out. And now I close off this valve, and I can turn this thing off. And now there shouldn't be such a disparity in how they fall. I asked for a feather. Okay, maybe we can do this again next time with a feather. But that's air resistance, and the effect is so large. No. Yeah, well, come on, I got a couple minutes for it yet. According to this, I still have 5.5 minutes. According to this equation, when you go twice as fast, you have 4 times the air you're pushing out of the way. This becomes extremely important when you're shooting a rocket from the Earth. You don't want to have that really, don't want to get it going really fast when it's still down in the atmosphere. Because if you do that, you'll lose a lot of energy before you get out of the atmosphere. So what you really want to do is get it slowly out of the atmosphere. And you see this when you watch the launches. You say, wow, that's slow. Yeah, you don't want it going too fast at that point. And once it gets out of the atmosphere, then you really get it going, accelerating a lot. You also come across this in automobile design. Because when you're going 60 miles an hour, something like 40 to 50% of your fuel is going to push that air out of the way. My Prius and many cars are designed, if you want better air, better fuel efficiency, you try to reduce this area. Now, the area here is the area that you'd get if you just had a sphere. But if you make it into something that's streamlined, then the actual area you plug into this equation is different. Because the air is not just bouncing straight back. It's now being deflected off like that. And so you streamline a car in order to reduce the effective area. And trucks do this now. There's a picture in the book about a truck. So here's the cab of the truck. And here's the back of the truck. And what they do is, this is a very simple thing. And it was adopted very quickly. And the reason it was adopted very quickly is that most truck drivers pay for their own fuel. And so it turned out if you just put a piece of plastic here so that the air coming would be deflected like that instead of bounced right back, that you reduce the air resistance and you'll get better mileage, which means more profit, which means more toys to bring home to your kids. So air resistance is a major problem. It's also tire resistant, but reducing air resistance, and if you want to save some fuel, go a little bit slower. When I wanted to see if I could get 50 miles per hour out of my Prius, really, it says 60, I knew I couldn't get that. I wanted to get 50. I was able to do it on a several 100-mile trip, but I was careful not to go over 55, because I know this effect is a big effect. Okay, we get into nukes on Tuesday.